Hi boys and girls. This video comprises the lecture for section 9.4 entitled Comparison of Series. In this section we're going to study two more convergence tests, and they're both comparison tests. We'll start with the direct comparison test. For the convergence test developed so far, the terms of the series have to be fairly simple, or the series must have special characteristics, for example, a geometric series or a p-series, in order for the convergence test to be applied. A slight deviation from the special characteristics can make a test non-applicable. For example, in the following pairs, the second series cannot be tested by the same convergence test as the first series, even though it is similar to the first. Here we have a geometric series 1 over 2 to the n, which of course can be written as 1/2 to the n, where r is 1/2, and we know this converges, but n over 2 to the n is not a geometric series. However, we might wonder if this series converges or not. In the second example, 1 over n to the third is a p-series, where in this case p is equal to 3, but the series 1 over n to the third plus 1 is not a p-series, yet we might want to have a way to determine whether or not this series converges or diverges. For number 3, we have a series n over the quantity n squared plus 3 squared. It's easily integrated, so we could apply the integral test. However, b sub n equals n squared over the quantity n squared plus 3 squared is not easily integrated, yet we may wonder if this series converges or diverges as well. Therefore, based on the fact that we do have series that do deviate from the known convergent or divergent series, we have the direct comparison test, which will allow us to make some assumptions about the convergence or divergence of these types of series. So in this section, we'll look at two additional tests for positive terms series. Again, we're dealing with just positive terms here. These two tests greatly expand the variety of series you are able to test for convergence or divergence. They allow you to compare a series having complicated terms with a simpler series whose convergence or divergence is already known. So that brings us to theorem 9.12, the direct comparison test. Let 0 be less than a sub n be less than or equal to b sub n for all n. So first of all, everything is greater than 0, meaning that the series has to be positive. And then we're saying that a sub n, term for term, is going to be less than or equal to the series b sub n. Therefore, if the series b sub n converges and a sub n is less than b sub n, term for term, then a sub n must also converge. That means that you have, perhaps this is your b sub n series converging, and then a sub n term for term is less than b sub n, it must therefore also converge. That's the idea. Now let's look at the second point. If a sub n diverges, and in this case that b sub n is greater term for term than a sub n, then b sub n must also diverge. So in this case, we would have a scenario like this, where let's say a sub n diverges, this is a sub n, and b sub n we know is greater term for term than a sub n, it must also diverge. That's the idea. Now you can probably guess that we're going to be comparing these more complicated series to simpler ones like geometric series or p-series or the harmonic series, ones that we know for certain converge or diverge. So let's do a couple of examples to see how this is going to work. In example 1, we're going to use the direct comparison test to determine the convergence or divergence of this series, 1 over 2 plus 3 to the n. Now you can see that this is really close to a geometric series that could be of this form, 1 over 3 to the n. In fact, let's let that be the one that we compare it to, n equals 1 to infinity. And I'll rewrite this as n equals 1 to infinity, 1/3 to the n. Now that tells us that r is 1/3 And for geometric series, when r is between 0 and 1, or at least the absolute value of r is between 0 and 1, we know that this series definitely converges. Now, let's compare it term for term to our series, the one that we're wondering about its convergence. So starting with n equals 1, for the known series that we have, we would have 1/3 plus 1/9 plus 1 over 27, etc. Now let's look at the terms of this series. For n equals 1, we're going to have 1/5, 1 over 2 plus 3 to the 1. For n equals 2, we're going to have 1 over 2 plus 9, which is 1 over 11. And for n equals 3, we're going to have 1 over 2 plus 27, which was 1 over 29. Now you can see term for term that our series is smaller than the known convergent geometric series that we're comparing it to. Therefore, by the direct comparison tests, we can say that our series must converge. You don't always have to generate a few terms and look at them term for term. Often you can just look at something like 1 over 3 to the n and just know for sure that it's going to be greater than 1 over 2 plus 3 to the n. Remember that when the denominator of a fraction is larger, the fraction is always smaller. So even though I'm generating a few terms so you can see how the comparison works, you may have been able to look at this from the very beginning and know that each fraction term for term of our series here was going to have to be smaller than this one because we're increasing the denominator by 2. A larger denominator makes a smaller fraction. So that's how you use the direct comparison test. Now let's do another example. We're going to determine the convergence or divergence of the following series. Let's rewrite this as 1 over 2 plus n to the 1/2 power. Now once I write it this way, you might see that it's very similar to this series, n equals 1 to infinity of 1 over n to the 1/2 power, which is a p series. A p series is when if p is greater than 1, then the series converges. If it's between 0 and 1, if p is between 0 and 1, then the series diverges. So notice in this particular case, we can see that we have a known divergent series. For us to use the direct comparison test with the series that we're looking at, we would need to be able to show that term for term that our series is greater than the known divergent series. Then we would know for sure that our series must also diverge. So let's try a term for term comparison. When n is equal to 1 here, we have 1. When n is equal to 2, we have 1 over the square root of 2. When n is equal to 3, we have 1 over the square root of 3 in the known divergent series. Now let's look at this series, and again, term for term, make a comparison. We have 1 over 2 plus 1, which is 1/3, and then for n equals 2, we have 1 over 2 plus the square root of 2, and then for n equals 3, we have 1 over 2 plus the square root of 3. Now, as we're comparing these term for term, and we're wanting to see that our series term for term is larger than the known divergent series, we can see that this is not the case. 1/3 is not bigger than 1. 1 over 2 plus the square root of 2 is not larger than 1 over the square root of 2. Increasing this denominator actually makes it a smaller term. Similarly, for the third term, 1 over 2 plus the square root of 3 is not going to be larger than 1 over the square root of 3. So comparing this series to this p series did not help us determine the convergence or divergence of our series. What to do, what to do. Even though comparing our series to this p series did not show convergence or divergence of our series, we don't give up. We still suspect that this is probably a divergent series. Let's compare it to another series, and for this particular series, I'm going to change colors just for dramatic effect. We're going to use the harmonic series. n equals 1 to infinity of 1 over n. Now this is still a p-series. It just means that p is equal to 1, but that still gives us a known divergent series. And for this term by term comparison, I'm going to convert these denominators in my series to decimals. So going back to the denominators of my series, I started with 1/3, then 1 over 2 plus the square root of 2, which is equal to 3.4. This is just the denominator now. And 1 over 2 plus the square root of 3 is about 3.7. Now, if I had kept this series going, let's go another few terms, and I'll just kind of come down here, plus 1 over 2 plus the square root of 4, which of course is a denominator now of 4, 2 plus 2, which is 4. And then let's go a couple more terms, 1 plus 2 plus the square root of 5, and 1 over 2 plus the square root of 6. I'm not exactly sure what I'm saying, but hopefully just notice what I'm writing. And this denominator will be 4.24, and this one will be about 4.45. Okay, so we have a new series in town, the harmonic series. Let's compare this term for term with our original series. And this little segue in the middle did not bear fruit or pan out, but we do not give up. We compare it now to this series. Obviously, for n is equal to 1, we have 1 as the first term of this series. Compared to 1/3, this is not bigger, okay? Now let's say for n equals 2, we have 1 over 2, which is 1/2. Compared to this term, again, this term is not larger. Its denominator is still smaller than this denominator, which is 2. The third term would be 1 over 3. Again, that's compared to this third term, which is still not smaller because the denominator here is 3.7. A larger denominator makes a smaller fraction. So again, we have not seen that these terms are larger than our known divergent series, but look what happens now. When n equals 4, the next term in our series is 1/4, and look at the fourth term in our series here. They match exactly. The fifth term, 1/5. Now look at the denominator. Now that this square root is having an effect, and it's actually going to term for term subsequent to the n equals 4 term, now give us a denominator that is smaller than the one in our known divergent series, giving us a fraction that is larger. 1 over 4.24 is a larger number than 1/5. Of course, if I go out one more term, 1/6, you can see that the denominator here is 1 over 4, the fraction here is 1 over 4.45. This is now bigger. So these two terms became larger than the fifth and sixth terms in our divergent sequence series. And you can probably guess that that pattern is going to continue. So even though our first three terms were not larger and did not prove divergence, the fact that after n equals 4, after that point, for the rest of the terms from 5 to infinity, now we have terms that are larger. So with our known divergent sequence, let's just pretend like this is the picture of the divergent sequence. Our sequence, first of all, was smaller, but then when we got to the fourth term, it became larger and will continue on to infinity, being larger term for term than our little 1 over n series. Therefore, after n equals 4, we're pretending like this graph has something to do with what I'm saying here, just to give you a visual. We can see that the series that we're testing against the harmonic series will be larger term for term from term 5 and on. Therefore, ultimately, it does diverge by the direct comparison test. So this is a good example of not just looking at the first couple of terms. You might be able to see a pattern that develops where eventually, after a certain number of terms, things change. Well, since we're going to infinity, what happens with these first few terms? Who cares? We're interested in what happens when x is approaching or n is approaching infinity. And, after the first few terms, we can see that our series was larger than the known divergent series, the harmonic series. So remember that both parts of the direct comparison test require that one series a sub n is less than or equal to b sub n, term for term, or at least after a certain number of terms. Informally, the test says the following about the two series with non-negative terms. If the larger, quote unquote, larger series converges, the smaller series must also converge. And point two, if the quote unquote smaller series diverges, then the larger series must also diverge. That's the direct comparison test in action. Let's now take a look at the second comparison test. Now we're going to discuss the limit comparison test. Often a given series closely resembles a p-series or a geometric series, yet you cannot establish the term-by-term comparison necessary to apply the direct comparison test. Under these circumstances, you may be able to apply a second comparison test called the limit comparison test, which brings us to theorem 9.13. It says, suppose that both of your series, a sub n greater than 0, both of your series are greater than 0. A sub n is greater than 0, b sub n is greater than 0. And the limit as n approaches infinity of a sub n over b sub n is a limit. It converges to a number that is both finite and positive. So you take the limit as n approaches infinity, and if you get a number that's not infinity and it's positive, then the two series either both converge or diverge. So a sub n is the one that is unknown, and you're going to compare it to a known series, whether it's divergent. So b sub n is the known one. You make a ratio of the two general terms and take the limit as n approaches infinity and look to see what you get. If it converges to a positive finite limit, then the two series go together. They both converge or they both diverge. So let's see how this one works. Now we have example 3 using the limit comparison test to show that the following general harmonic series diverges as n goes from 1 to infinity of 1 over an plus b. Now, it probably seems obvious that we're going to compare this to the harmonic series, which is 1 over n. And of course, this is a known divergent series. So, using the limit comparison test, I'm going to take the limit as n approaches infinity of my unknown, which although we might already know that this one diverges, we're going to pretend like it's unknown, over my known. If I get a limit that is positive and finite, then the two series go together. And in this case, since I am comparing it to a known divergent series, then that will tell me that this series also diverges. So let's go through the process of seeing how to simplify this ratio and then, of course, take the limit. Remember that with a complex fraction, 1 over an plus b divided by 1 over n is the same as 1 over an plus b times n over 1. So this simplifies to the limit as n approaches infinity of n over an plus b. Of course, if you plug infinity in now, you get an indeterminate form, infinity over infinity, which means you can use L'Hopital's rule, or you can do the trick where you divide every term in the ratio by n and simplify it that way. Whichever way you want to do it, I think L'Hopital's rule is a little bit quicker here, so I'm going to do that. If I take the derivative of the numerator and denominator, I end up with, remember that a and b are constants, so this ends up being 1 over a. Since a is positive, my limit as n approaches infinity, I should go ahead and say now I'm taking the limit, no place to plug in here, infinity, in, it doesn't matter. Since I converged to a number that was positive and finite, that means that the two series go together. And since we know that 1 over n diverges, now we also know that 1 over an plus b diverges. And that's how you use the limit comparison test. Let's try it again. With a little segue here for further explication. The limit comparison test works well for comparing a messy algebraic series with a p-series. In choosing an appropriate p-series, you must choose one with an nth term of the same magnitude as the nth term of the given series. For example, if we were wondering if this converges or diverges, we would compare it to the known p-series here, 1 over n squared. Notice we chose n squared because it has the same magnitude as our given series. Now let's look at the second example, 1 over the square root of 3n minus 2. We're going to compare it to this p-series, 1 over the square root of n, because it has the same magnitude or degree of the given series. Similarly, looking at our third example, n squared minus 10 over 4n to the fifth plus n cubed, we're going to compare it to n squared over n to the fifth, choosing these two exponents because those are the degrees of the numerator and denominator. Of course, that simplifies to 1 over n cubed. This is the same magnitude as the original function that we're wondering is convergent or divergent. In other words, when choosing a series for comparison, you can disregard all but the highest powers of n in both the numerator and denominator. Now, let's do our last example. Example 4, using the limit comparison test to determine the convergence or divergence of the series the square root of n over n squared plus 1 as n goes from 1 to infinity. Now, again, let's just look at the highest powers of n in the numerator and denominator. This is like n to the 1/2 over n squared blah blah blah, which is like a 1 over n to the 3/2 power expression. So this is the p-series that we're going to compare it to. So let's set up our ratio. We're going to have our series, which is n to the 1/2 over n squared plus 1 over, comparing to the known p-series, 1 over n to the 3/2 power. And of course we're taking the limit as n approaches infinity. Now simplifying this means, of course, that we're going to multiply by the reciprocal of this denominator, giving us the limit as n approaches infinity of n to the 1/2 over n squared plus 1 times n to the 3/2 over 1, which gives me the limit as n approaches infinity of n squared over n squared plus 1. Now it's time to try to take the limit. Of course, plugging infinity in right now gives us an indeterminate form, infinity over infinity, but instead of using L'Hopital's rule twice here, I will go ahead and use the process of dividing everything in the rational expression by n squared, which ends up giving me n squared over n squared over n squared over n squared plus 1 over n squared, which means now I'm trying to take the limit as n approaches infinity of 1 over 1 plus 1 over n squared. Now when I plug infinity in, this becomes a 0 term, which means that my limit is 1. Since this is not infinity, it's finite, and it's positive, this means that these two series go together. Since our comparison series converges, then that means the one that we were trying to test also must converge. Again, that is how we use the limit comparison test. Kind of fun. All right, now let's look at our chart one more time. And this is just kind of taking you through where we are thus far in our knowledge of series, how to test for convergence and divergence. We've discussed the nth term test for divergence. We've also looked at geometric series, telescoping series, p-series. We've discussed the integral test and also the direct comparison test and the limit comparison test. So in the next two lectures, you'll be looking at alternating series and the root and ratio tests. So that's where we are, and I found this humorous, and I thought you might too. God bless you, boys and girls.